Thank you, Mike. Thank you, everyone, for coming here. Can you hear me? Good. Yeah. Perfect. Okay. So I'm finally a postdoc here. So I'm going to tell you about this project we've been thinking out in the last couple of years, and then some recent result that we got. And so the title of paper is something along the line of polynomial path lower bounds in graph streams. Ideally, it should have been something more like towards polynomial paths, because we answered the question we wanted, but there are lots of open questions still open, and I'm sure there will be some follow-up. We should specify proving polynomial path lower bounds in graph stream wasn't even a hard problem. We knew how to do that before even we knew about graph streams, like 30 years ago. It's about some specific family of problems that have a very well-defined technical definition. We wanted to prove lower bounds for that problems. Okay.
So polynomial is n to the epsilon?
Yes, n to the epsilon, yes. Some small polynomial. Basically, important thing is above log n. Okay. Then finally, there is a third part to the paper about application to submodular minimization. It's a very interesting problem on its own. If you are interested, we can chat about it, but I'm not going to talk about that here today. Cool. So, a very quick background. So, the streaming model is a model of computation which tries to focus on the following two aspects of computation. One, when you have a very small memory to work with, much smaller than your input. And when you don't have random access to your input, when you can only access your input in a sequential manner. So when does this situation happen? The typical example is when you want to process some packets in a network. You have a router or a switch. Its memory is much smaller than all the packets it's ever going to see. And also the packets are coming in a sequential order. When they pass, you don't have any access to them. But for this talk, it actually makes more sense to think about application of a streaming to processing massive data sets. When you have a very large input, think of terabytes or petabytes of information, and you want to run some typical algorithm on that. And such an input, you cannot just load all of it in your memory and then work with a random access algorithm. You have to do something different, and a streaming algorithm tends to be very good here. And with this view, actually, you can think of, you can actually access your input multiple times. It makes sense to make a couple of passes over your input if you cannot solve it in just one pass. Okay? I'll define the model formally in a second. So streaming evolved primarily 20 years ago, actually, with a paper by Noga and others. Its roots are actually even way older than that in median finding algorithms, things like that. And for graph streaming that I'm going to talk about, it was formalized by Feigenbaum et al. In 2005 or so. So now what's the model formally? Let's say I have a graph G. Its vertices are 1 to n. N is known to the algorithm, so the algorithm completely knows the vertices of the graph. Okay? The edges are unknown to the algorithm, and they are written in some arbitrary order, let's think in a large array or in a sequence. This is what we are going to call a stream. Okay? And then a streaming algorithm is an algorithm that have a very limited space. It can just basically read this stream in this order. So the head of the algorithm can first read E1, then it reads E2, E3, and you continue like that until you make one pass over the stream. And here the working memory of a streaming algorithm is small. Okay? And so this constitutes one pass. After it's finished, you might want to continue actually doing the same thing from the beginning again. So you can again read E1, E2, make another pass, and then solve the problem at the end. One thing I want to emphasize, there is no onlineness in this model. The graph is there, it's fixed. It's not created in an online fashion. That's the online model. Streaming, the graph is there, you just want to process it in a streaming fashion. Make sense? And now what are two main factors in this model? Well, one is the space of the algorithm. We want the size of the working memory of the algorithm to be small, ideally much smaller than the input size. Okay. And another factor is that we want to limit the number of passes you make over the stream. If I allow you to make many number of passes, then it more become about bounded space computation as opposed to streaming. You want to do maybe one, ideally one, maybe if not, log n pass, not a lot. And just one thing to mention, a graph with n vertices has at most order n square edges. Even if there are some weights, order n square polylog n bits are enough to represent a graph. So if my streaming algorithm has something like order n square space, the problem is completely trivial. You'll just store all of the input in one pass, and then you do whatever you wanted with it locally after the first pass. So it's only interesting when your memory is much smaller than n. And when this happens, actually, you may need to pay it with larger number of passes. And so I'm going to focus on this family of streaming algorithms, typically called semi-streaming. Their space is n polylog n, and you are typically interested in using up to polylog n passes with these algorithms. The reason to go with n polylog n is basically reduce the graph from its edge space to something which is proportional to the number of vertices, okay? Which is typically even the size of the answer of the solution we care about. For example, if I want to find all connected components in my graph, my output itself is something proportional to number of vertices, and we want to use a memory which is not much larger. Now I'm going to mostly focus about semi-streaming algorithms here. I want to emphasize these are not all streaming algorithms. Even you may have a streaming algorithm, for example, that uses n to the 1.99 space, and let's say 2 to the square root of log n passes. That's very interesting on its own, because you have to do some non-trivial work to get such an algorithm. Okay? This is semi-streaming is basically the limit of such algorithms. Anything in the middle is completely interesting. Okay? So the talk is going to be a bit long in the details, requires a bunch of background before I can say something useful about our result. So before I bore you with that, let me just tell you what are the results. If they made sense, perfect. If not, I'll spend the next 20 minutes trying to explain them. So our result basically is that a semi-streaming algorithm for problems such as ST maximum flow, ST minimum weight card, and lexicographically first MIS requires n to the 1/5 passes over the input. Okay. So the definition of the first two problems should be clear. The third problem, independent set is a set of vertices that do not contain any edges inside it. Maximal means that you cannot extend it by adding one more vertex to it. This is very different from maximum. And finally, lexicographically first means that it is among all maximal independent sets, if you write its vertices in its lexicographical order, this appears first.
This is with memory n log n?
N polylog n, yes. And I'm saying at one point of the trade-off, we give a whole trade-off basically. So algorithm with close to n square space, n square divided by polylog n will need polylog n passes. Okay.
There is no runtime bound on what the algorithm does.
Good, yeah. We can just completely ignore what are the runtime of the algorithm. So all these problems are polynomial time solvable. And lexicographically first semi seems to be actually a very interesting problem in the streaming model, which I'm going to explain later. Roughly for the same reason people have studied first in the PRAM like 30 years ago or something. And just to mention, the previous best lower bound for all these problems was just omega log n passes. Finally, the main contribution was to basically try to extend these lower bounds that only work for log n passes, just extend them to allow you to prove something with even polylog n or even close to some small polynomial number of passes. And just looking into the future, the technical question here is something like this. Is there a graph problem which in the two-party communication model, you can solve it with a very small amount of communication, proportional to number of vertices, but in the streaming, it requires you to lot a lot space in a small number of passes, which is polylog n. If it made sense, perfect. If not, I'm going to try to explain this later. Okay. But this is basically our main result. Is there any question?
So if you wrote the natural graph problem, then I presume some pointer chasing will do it, right?
Yes, you can do some sort of pointer chasing there, or yes, okay. But I don't see a way of doing pointer chasing basically for basically that's what we want to do actually.
So this is the candidate, pointer chasing?
Yes, some sort of pointer chasing is going to be. We want to make it such that you can actually solve problems such as maximum flow and minimum cut using that type of pointer chasing. Good. And a natural problem is that actually this lexicographically fair semis that I mentioned have this property. The way we get all our other results is basically just reducing them to this problem. So now let's try to make sense of this result.
When you say natural, it means that it's known for other problems.
Not really. I think you can cook up something maybe, but no, I don't know actually something just right there that you can create such a graph problem.
So this is the first such separation, something that can be done in communication complexity,
I think
but
so.
cannot be done in this sense.
I think so, yes. We didn't really think of it as doing a separation there. This appeared as some technical barrier, and then we wanted to solve it to get the lower bounds for these flow problems that we care, but yes, probably. Good. So now let's try to make sense of what is happening in the streaming model. Let's say, so in the semi-streaming, we fix the number of the space of the algorithm to be n polylog n, so the variable is basically the number of passes. Okay. So already with one pass, we know tons and tons of very non-trivial algorithm. You can solve many different problems, such as, for example, getting a 2 plus epsilon approximation to weighted matching, or 1 plus epsilon approximation to minimum cut, even weighted. In this model, with just one pass and n polylog n space. And there are tons of other results here. But we also know that there are lots of problems that we cannot solve in this model. Okay. Maximal independence set is one example that we know at least in one pass you need to spend omega n square space. But then when this happens, people start to looking at multiple passes. And up to log n passes, we know a lot of results. Nearly a very large family of problems can be solved here. One very interesting example is that if you want to solve an exact global minimum cutoff, an unweighted, undirected graph, you can do it in just 2 passes. In fact, actually, this algorithm is with math and others, and their result is not for the streaming. They give some structural result about min cut. If you merge it with the techniques we know in the streaming, it immediately gives you such an algorithm, which is very surprising. No? In just 2 passes over the stream, you can solve the min cut problem. Another example is, for example, with log n passes, you can solve the MIS problem. We prove that if you have this restriction of lexicographically fairs, then it is hard. Without that, you can actually solve it in log n passes. So it seems that semi-streaming algorithm with log n passes can solve a very wide range of different problems. Okay. But there are some problems there that we actually do not still know how to solve. Okay. Some important open problems here is then, can we solve directed reachability? So basically connectivity in a directed graph, ST maximum flow, shortest path, or can we simulate random walks in this model? Okay, in a small number of passes.
All the algorithms are randomized, or you consider also deterministic?
No, we consider deterministic. Most of the result I'm talking about randomized, but some of them are actually deterministic also. Like, for example, minimum spanning tree, I think you can find it exactly just deterministically. Or connectivity, for example, a spanning forest, you can always find it deterministically also.
But this coloring was randomized?
It is randomized, yes. It is randomized. Good. So these are some set of problems that we actually care about, and some of them have been open since the first paper that introduced a streaming model. How can we solve them in a small number of passes?
So this is all up to log n passes?
Yes, up to log n passes we can prove lower bound for all of them. We don't know. And these are some summary of the lower bounds. And interestingly, some of these problems admit very non-trivial algorithms which use something like n to the 2/3 passes, for example. So you can do something completely non-trivial, for example, for reachability. It's not log n, but it's not n also. So you can do something around here. Okay. But basically now we do not know how hard or easy are these problems. They are harder than log n. They seem to be easier than n, but we don't know where they are really. Now one question, do we know any hard problem? Is there a problem that basically we cannot do anything useful in the streaming? Yes, there are such problems. One example is, for example, computing an exact maximum click or independent set. You can prove that it almost requires n over polylog n passes. Okay. Another thing, for example, whether my graph has a triangle or not. So you can prove something which basically these problems require n over polylog n passes. So then what's going on? Basically, we have some lower bounds here between 1 and log n. We have some lower bounds all the way down there. Prove that even n passes, almost n passes are needed. But we don't have a lot of result happening in the middle. You don't know a problem, for example, that you can prove it really needs n to the 1/3 passes.
Naturally, right?
Yes, you can always, yes, those n pass lower bounds, you can just say that, okay, we proved it up to root n. So, yes, you can just reduce the size of the graph a bit. Yes, I mean. And so our goal is basically try to prove lower bounds for problems that are appearing here. So now let me tell you briefly what's going on that we can prove lower bounds here, we can prove lower bounds there, what is happening in the middle. And to do that, let's just look at what are the techniques for proving a streaming lower bounds. So almost all of the graph streaming lower bounds are proven using communication complexity. In very different models, the most basic version is just to look at two-party communication model. And there are many other models studied, mostly number in hand, or always number in hand, if you look at multi-party. But in this talk, I'm just going to basically talk about two-party and a very simple four-party model. Okay, so what is the communication model, basically? For a graph problem, you have two players, Alice and Bob. Alice gets to see some set of edges over 1 to n, vertices 1 to n. Bob gets to see another set of edges from 1 to n over the set of vertices 1 to n. And your goal is to solve some graph problem over the union of these edges. Okay. For example, find the minimum cut in this graph. And then the players can communicate back and forth with each other. And then you want to limit the amount of communication. And basically, let's define communication complexity of a problem here. It's the minimum amount of communication Alice and Bob need to do such that they can solve the problem with probability 2/3. Okay? Yeah.
Public or private randomness?
Doesn't matter, public randomness. They are additive factor of log n. Good? So why is this useful? Well, any streaming algorithm is basically a communication protocol in its own. Just think of this scenario. Suppose Alice has these edges of this communication problem. She can just basically create a stream which half of it is edges that Alice have, the other half are the edges that Bob has. Then Alice will just going to run the streaming algorithm on her part of the input on the stream, look at the state of the algorithm, send it to Bob. Bob is just going to continue running that. We'll send it back to Alice, and then this way they do one pass of the streaming algorithm. And the space, the communication for this one pass is just proportional to the space of the algorithm. You do this many times, at the end you can solve the problem. And because a space is reusable, but communication is not, so if the space of the algorithm is S and you do it P passes, your communication is going to be roughly P times S. So then we are done, basically. A space complexity of a p-pass algorithm is 1 over p times its communication complexity. So then let's just try to prove communication complexity lower bound for a problem, and it's done. So these problems that I mentioned that have n over polylog n pass lower bounds, they're basically like this. You take your graph problem, you prove that its communication complexity is omega n square, and then it immediately tells you that if your streaming algorithm uses n polylog n passes in polylog n space, its space has to be, its pass has to be n divided by polylog n. Make sense? So what is bad about this approach, basically, is that you can do this thing for a problem which is really too hard for the streaming to begin with. So let's say I'm going to call a problem too hard, basically, if its communication complexity is more than n times polylog n. Okay. If a problem doesn't have this property, this lower bound approach is not going to give you anything that useful. Okay. But if a problem has such a large communication complexity lower bound, it's probably, to begin with, it's not suitable for the streaming model. Yeah.
So what do you mean by the communication complexity? Is it when you partition the input
In the worst case.
In between two.
first half and second half, or in the worst case, or just for
Yeah.
context?
Yes.
By the way, is it clear that n passes are enough for everything?
Good.
Because the input size is like n squared. That's,
So the way streaming is actually defined, you only measure the space during the stream. Let's say there is a computer at the end which has an unlimited memory. In n pass, you can basically shift all your input with n space to that computer or processor at the end. Okay. So n pass and n space will allow you to send all of your input to that processor there, and that one has unbounded computational power, and you can solve it there. So n pass in that sense is always.
it's not just memory. Okay.
Okay, but you can of course define the streaming such that you don't have such a thing, and you work with bounded.
This is just for, this definition is just for proving lower bounds. It's not really.
Yes, I think so. Another reason is that you don't want to look at bounded computation, bounded space computation. You want to have some difference between this model and, for example, log space algorithms. No? If I allow, let's say, polynomial passes, then it's not that different from an algorithm that just uses a smaller space. Okay, but I agree, n passes is not some sacred number. You can change it, and you can prove something.
It seems to be, because it's a graph problem, right? And the input is actually n squared and n.
No, so if I give you p passes with this definition that I said, input divided by p space is always enough. Make sense?
With this definition.
Yes, but I agree. It might not be the best definition, really.
No, what she means that in a graph problem there are n square inputs, so you could consider up to n square passes without getting into complexity low bounds, into complexity barrier.
Sure, okay. So I was looking at semi-streaming algorithms also that use at least n space. And there is some distinction between algorithms that use less than n space, because then it's about, let's say, vertices of the graph. For example, you want to estimate size of some problem. So let's say you want to estimate size of the minimum cut in your graph. Then that problem, it makes sense to look at it even when you have order log n. Yes, and then definitely you can look up to n square. I was assuming that your algorithm at least uses n bit of a space. Okay? Yeah.
How hard is finding a triangle? Is it too hard?
It's n square, yes. You can prove, there is a simple reduction to set disjointness, proves that you need n square, basically, and so.
Okay.
So what are some examples of problems which are, want to say they are not too hard? Problems such as reachability or shortest path. Okay? Can think of in this model, both of these problems, you can solve them with n log n communication. Does it make sense? For example, for shortest, you can really run the extra algorithm with n log n communication. There is another thing, is that there are some problems that we don't know what is their complexity. For example, a problem such as perfect matching or maximum flow. You can prove some non-trivial upper bound, n root r on n to the 5 over 3. Okay. And currently, we do not know lower bound there. What it means is that if you want to use this approach, you have to prove, for example, if I want to use this approach for the perfect matching problem, I first have to prove a lower bound for this problem, which seems way harder than proving a lower bound for streaming problems to begin with even. Okay. And even if you do that, what is this approach going to tell you is that if your streaming algorithm use n root n space, you cannot prove any lower bound for that. So it probably you can say that maybe I have a streaming algorithm that uses n root n space and just 2 passes and solve the matching problem, which will be very surprising if such a thing happens.
How do you prove logarithm has lower bounds using this?
Good, I'll tell you in a second. Good. So now let's see how to prove lower bounds when you have a small number of passes, okay, and up to log n passes. You again use communication complexity, but now this time you also bound the number of rounds the players are talking to each other. Okay. So now I want to say that a protocol has r rounds. If Alice and Bob send at most up to r messages to each other, the size of the message might be long, but they are only going to interact with each other r times. For example, here this is a 5-round protocol. Okay. Now r-round communication complexity, then again you can define it as before among all the protocols that only use r rounds. And why is this any better? Well, r-round communication complexity as before is going to bound the space complexity of algorithm that use up to, let's say, r over 2 passes, or r over 2 minus 1. So in that sense, this is good. And also what is better is basically for some problems, your communication complexity in r rounds must be much, much higher than your communication complexity without any restriction on number of rounds. A typical example is this pointer chasing problem that Mark mentioned. So what is the problem? Let's define it one way as a graph problem in k layers. So let's say I have a graph which has k layers of vertices. Each of them have m vertices. Then each vertex in each layer has one edge or one pointer to the next layer. Now these Alice, let's say, have the pointers between the even layers, and Bob has the pointers between the odd layers. Okay, so this is just a standard pointer chasing problem. What do you want to do? You want to start from one specific vertex, let's say the first vertex here, follow these pointers and see where you're going to end up. So you'll end up somewhere around here. So that's the whole communication problem. Definition clear? Good. So this is a problem which is easy if I allow you k rounds of interaction between the players. So Bob has these edges. Let's say in the first round, Alice doesn't say anything. The second round, Bob will tell you go from here to here. It will give you this pointer. Then the next round, Alice tells you this pointer. You continue doing that. Then in a small number of rounds, if you have k rounds, you can solve the problem with just k log m communication. And what is interesting is that if you don't have k rounds, then you need something like m over k communication. There is no way for you to shortcut the number of rounds. And such results have been known for a very long time. Okay. So now reachability. So this pointer chasing actually is basically the reachability problems in a graph. No? If this green vertex is vertex S, I want to find what is the vertex in the last layer that this vertex can reach.
So this is easier because the degree is 1.
Yes, thank you. So can I just use this problem on its own to get a lower bound? The answer is no, because as Gilad said, this graph is very sparse. No? It only had one edge per each vertex. So the total size of this graph is order n. You can just store the whole graph in order n space. Remember, we wanted to prove a lower bound for algorithm which use super linear in n space. So then you want to have this pointer chasing, which basically uses omega n space, little omega of n space. Now it's where the problem starts. There are tons of different variant of pointer chasing that I know at least in the streaming people looked at. And all of them have this property. Instead of using one pointer per each vertex, you are going to use a lot of pointers. Okay. And you are still going to let these pointers to be edges of your graph. Okay. So let's see how do they work, for example, for proving a lower bound for reachability. Well, let's say instead of one pointer for each vertex, I'll give L random pointers to the next layer. And we want to follow all these pointers. I want to see if I follow all these pointers, what are the vertices I'm going to reach at the end. And if I want to do it in a small number of rounds, and if I give L pointers to each vertex, then you expect the problem to become L times harder. No? Want it to become M over K times L. This is completely valid. You can say things like this. Up until the point that these pointers that you are increasing are not going to span the whole layer completely. So
Why not L to the 3 times harder?
it shouldn't become that much. No, M times L is your input. So
But they're K lower. Okay, maybe.
okay. I mean, the total size of your input is something like K times M times L. So it cannot become that hard. But you see, if some situation like this happen, then this problem is not that hard after this layer anymore. You had some guess what you may need to solve something to see what is happening here, but after that you'll just reach everything. And what is the problem with this is that if each vertex is choosing L random pointers to the next layer, what is going to happen is that in K rounds you are going to span roughly L to the K vertices.
So what's the answer? If you get something with an out degree greater than 1, you can output anything?
No, you have to output all of the things that,
All of
the pointers, yes.
And the
Okay.
input is not, oh, okay.
So basically all of the things that you reach with those pointers. As a reachability problem is that how many vertices, what are the vertices this guy can reach? Okay. So if there is a path, you have to output it. Good. So if I have K layers, I'll reach something like L to the K in K steps. And so to prove a lower bound here, you have to set K to be, so you have to set L to be something like N to the 1 over R, such that N to the 1 over R to the power R is still less than N. And if you do that, the lower bound this thing is going to give you is something like N to the power 1 plus 1 over R. Make sense?
So you could hope to do things not randomly, maybe.
Yes, you may want to do. You may want to connect things not randomly, and something like that may work. Okay. The thing is that all of these approaches that are trying to just put some edges there seem to fail those type of pointer chasing lower bound. Once these pointers that you are going on start colliding with each other, okay, then you cannot continue proving things, at least here with those approaches. Don't know, maybe there is a way to not connect them randomly, and if there is a way, it should be by that, not randomly to the next layer. But then I don't know how to prove a communication lower bound in that setting. So what is the problem, or not really a problem? I think this, looking at communication complexity with bounded number of rounds, seems to be a better way of capturing the essence of a streaming algorithms. Okay. But the thing is that now these techniques that we have by just directly trying to massage this pointer chasing only prove things which look like N to the 1 plus 1 over P space for P-pass algorithms. This is bad, first because after log n passes they don't work anymore. And even before log n passes, let's say if I have 1,000 passes, they prove something which is very weak, N to the 1.001 space, which is not that interesting in some sense. And now, as Noga said, there is one inherent problem here, is that if you just start to try to encode these pointers by the edges of your graph, you roughly end up working with random graph. And random graphs for many graph problems are actually not that hard. Okay. So you want to try to maintain something which is actually not that random. So two ways of proving lower bound. Look at communication complexity without restricting number of rounds. It seems a bit going backward because we want to prove something simpler, but we are looking at a very strong computational model. Okay. The other way is to try to look at communication complexity with bounded number of rounds, which is more similar to streaming. Then basically just try to define some hard problem, which is basically try to extend the lower bounds here to work more than log n passes. And then one way to see that, if we want to start working on a problem here, is that can we design a lower bound for a graph problem which only requires order n communication, so the first technique doesn't work, and then try to strengthen the second technique to prove polylog n pass lower bound. Good? Basically, that's exactly what we are going to do. We want to prove some sort of pointer chasing so that you do not need to pay this exponential decay in the number of passes. And then as a result, this is the way we are going to get this n to the 1/5 pass lower bounds for semi-streaming algorithms for a stiff flow, estimated mean cut, and lexicographically first MIS.
Are there upper bounds for non-trivial upper bounds?
So this one has an order n communication protocol. These two have an order n to the 5/3 communication protocols. Okay, so there are some non-trivial upper bounds.
Okay, so this is not the n past the
No.
extreme point.
I don't know if these things have a better than n pass algorithm in a streaming. They have better communication protocols.
Yeah,
Okay.
but your point with the point
Yes.
there was
Yes, and this one certainly have both.
Do we know that they're like complete in the sense, like pointer chasing is often complete?
I don't know. I've never thought about that.
Like it's
Yes.
unclear if you get the upper bounds for those, it gives you upper bounds for like a large family of other streaming problems.
What pointer chasing though? Is there a generic definition of pointer
Yes,
chasing?
you had like 10, right? One of them.
Okay.
So it's basically whether
You'll
there are
get
reductions to
You'll get something for reachability if you prove that. I don't think pointer chasing is enough, for example, to prove something for flow. Basically, it means that is ST reachability can solve maximum flow?
Yeah.
I don't think so in a streaming setting. Okay. Cool. Okay, so basically, the way this thing works is that we want to do again pointer chasing. Let's try to define a new problem. Let's call it hidden pointer chasing. This is actually the way we come up with that problem. It's almost equivalent in its definition with lexicographically first MIS, but I'm not going to define it like that. I'm going to define it in its abstract form. It still involves chasing some pointers, but now at this time I don't want to just give these pointers as edges to the players. Okay, I want these pointers to be some concept in the graph which is not necessarily just edges. And then to do that, to find these pointers, I want the players to force the players to solve another hard communication task between themselves. When they do it, then they'll find a pointer and then they can move on with that. Okay. And I think a good part of this thing is try to identify this problem. When you have the problem, then the rest are not that hard. So what is the problem? First, let me define set intersection. I'm sure all of you will know that, but just quickly. Let's say I have Alice and Bob. Each of them give some subset of a universe of M. And I'll assume their input is such that they intersect in exactly one element. Okay. And then the players have to find that element. Like here, they have to find the element 5. They can do communication. This is basically the same as set disjointness problem. And we know by Rosberg result and others, this problem have communication complexity of omega m. Okay, without even restriction on number of rounds. Now let's use that problem and embed this and try to work with that problem and pointer chasing together to define this hidden pointer chasing problem. This is a problem we are going to work with 4 players. I think this should be doable even with 2 players, but 4 players. The problem is something like this. So I have 2 groups of players, let's say Alice 1 and Bob 1, Alice 2 and Bob 2. each of them is getting m instance, each group is getting m instances of set intersection. Okay, so this one is getting, let's say, 5 sets. This is 5 another sets. An intersection of each 2 of this thing is a unique element. The universe of these set intersection instances is again m. Okay, so if you look at these 2 players, or let's look at these 2 players. Look at the intersecting element in their input. It's a number from 1 to m. Let's say it's 2. So it will point to this instance here. Okay. Now I want you to solve the set intersection here. It will point you to another instance here. This is just a number. It will point you here, and then you move on like this. Does it make sense? Okay. So this is the problem, basically.
So this is about the worst case partitioning, I guess, of the inputs. Instead of partitioning the inputs half and half, you just partition each of them. It's a worst case partitioning of the inputs within the players.
That is, I'm not sure what you mean
Even if
actually.
you partitioned randomly, well, it wouldn't make so it's like revealing some constant fraction of the point.
Yeah, I think.
Still pretty
Instead of
broken.
partitioning the edges half and half, you partition every edge in a sense. So that's
But
the
if you
worst
took
kind
those
of
inputs,
partitioning.
made a soup, and divided into 4 groups, I think it would just make the problem constant factor easier.
Okay, that's it.
Yeah, I think so. Okay, so this was the problem. Did it make sense? And just to make sure, what is the communication model or pattern we want to talk about? Let's say the players in the first group, they can talk back and forth as much as they want. No restriction on number of rounds. We only care about how much they communicate. After they are done, one of them will send a message to the next group. Then those players are going to talk back and forth with each other. Then when they are done, one of them will send a message to the first group, and you continue like that. Let's call each of these things a phase, something exactly like a round. The only difference is that now these players inside one phase, these 2 players can talk back and forth with each other. So that's the phase. And again, it's very easy to see that if I give you k phases, you can solve the problem with order k times m communication. Okay? And this is easy in the sense that when you turn these instances to a graph, that graph is going to have k times m vertices. So with a communication proportional to number of vertices, you can solve the problem in k phases. But then what we are going to prove is that if you do not have that k phases, if you want to do it in k minus 1, then you need something like ms squared divided by k squared communication. Now you can see this is similar to a graph problem. It's a graph problem on something like km vertices. Okay. And by getting ms squared lower bound, we get some lower bound which is proportional to number of edges as opposed to vertices. Let me actually show you how to use this problem to prove a lower bound, let's say for maximum flow. Good. So let's say I have one instance of this problem. I want to turn it into a graph, an instance of a stiff flow problem. Okay. I'm going to take that instance of the problem. I'm going to create, I think, k plus 1 layers actually, not k layers. So I'm going to put these layers of vertices. Each of them have m vertices. Then let's look at the ith vertex in each layer. Okay. You connect it according to the set of the edges that, let's say, Alice 2 had in that set AI, and Bob 2 had in that set BI. And you do it for all vertices. I drew it for one vertex. In the actual reduction, you drew it for all vertices. So between these 2 layers, it becomes something very dense. Every vertex is roughly connected to tons of vertices, and to half of the vertices on the other side, almost. Okay. Then you'll get this very dense graph. And there are some extra edges with some certain capacities that are needed for the reduction, but those are fixed. They do not depend on the input. Okay. And why does this model the stiff flow? Let's just look at the flow problem. You start from S. You come here. There is just one vertex here that both Alice 1 and Alice 2 and Bob 2 had an edge to. All the other vertices here are only neighbor to one of these guys. That single vertex, so Now there is this vertex which also corresponds to the pointer of that problem. So to this guy you can send more flow than all the other vertices. So you send a flow here, these extra edges are going to take care of the remainder of the flow. And just to make sure, this is capacitated. Okay? So some of the flow will go here. The only vertex that has an excess flow is this guy, which was the pointer. So now the same thing happens. Then again, the only vertex in the next layer that have an extra flow is the pointer vertex. So you continue like that. At the end, everybody here will just send all their flow to T. By the way, these are all the same vertex. I just drew it in multiple places. There will be just one vertex here that can send an extra unit of flow directly to this guy. So if I recover the flow path, I can actually recover the final pointer in my graph. Roughly. Good? Then it's easy to see that actually if you have an algorithm, a streaming algorithm that uses smaller than k paths, something like k over 3 paths or something, it will give you a communication protocol for this problem with a small number of phases, and so you'll get the lower bound. By the way, the instance that I showed you had some problems such as having it was a multi-graph, it was directed, and also I had to find the flow paths. You can remove all of it. Okay, you can make it a simple undirected graph, and also you don't need to find the flow path. Just knowing the value of maximum flow will be enough for you to identify the pointer. And so you do that, the number of vertices in your graph is something like k times m, so you get a lower bound of m squared divided by k squared. If you do put these things there, do the calculation, which gives you any p-path streaming algorithm for max flow, and also by min-cut max flow duality for min-cut, requires n squared divided by something like p to the 5 a space. Okay. Why is this good? Well, so first, if you set your space to be n polylog n, you'll get something like n to the 1 over 5 passes are needed. And if you set your number of passes to be smaller than log n, actually it says that you almost cannot do anything. You need n square space, almost n square. So you have to store everything. This is the way to prove the lower bound.
You said that for finding the approximate maximum flow, it's much easier.
Min-cut.
Really needed it
So
exactly, right?
yes, this is finding the flow paths might be a bit hard, but finding the it's you can compute a cut sparsifier, okay, in just one pass, and then you're done. Okay.
Why did you pick up this 5?
Because the first one is
You are going to pay, so a space is reusable basically. 4 of them is because of this thing. My number of vertices is n. So I'll get n squared divided by k to the 4 because of number of vertices, and I lose 1 more because in each pass I'm paying in the communication proportional to the space of the algorithm. Communication complexity is k times larger than the space complexity. Okay, and that's why the 5 comes. I'm sure 5 is not optimal also. You should be able to reduce it. Okay, so let me very briefly tell you how we prove that lower bound for that hidden pointer chasing. It's actually not hard. It's easy in some sense. So this is the problem. We had these m different instances of set intersection, and we wanted to follow this type of pointers. Okay. So the first thing is that if you have m independent instances of set intersection, solving all of them is m times harder than solving one of them. These are these direct sum results that follow from just using information complexity. So we are good here. Then we want to do a standard type of round elimination. We want to say that if we do not solve, and I'll get back why it is solved, most of these set intersection instances in one pass or in general, then you can only continue the pointers one at a time per each phase of the algorithm. Okay. This is the same exact argument you do for typical pointer chasing, is that if you didn't solve everything, that pointer was uniform. You typically didn't solve it for that particular pointer, and so you cannot progress more than one pointer per each pass or phase. there is a problem. These two things do not match completely because you really don't need to solve the set intersection problem to be able to continue your pointers. Just think about it. Suppose I'll do a small communication between the players. I do not solve the set intersection, but I give you some sketch which does the following. For each pair of set intersection instances, I know, let's say, root n. So originally, this pointer is uniform. Suppose I do a small communication, and after that, instead of having a pointer which is uniform, it's just uniform in a much smaller space. So I didn't find the pointer. I didn't find the target element. I just reduced the uncertainty about it. I said it's one of these 100 other elements. If I do that, then the problem becomes easy. Okay? Because then I can only solve the problem for that 10 candidate for now and then continue. So what I need is that actually what I need from the first result is that if I do a small communication, not only I do not know what is the pointer, but I have no idea. It should be still almost uniform as it was before. Okay. So that means that we have to prove something for this solving of that intersection. Let's just define it a bit. So let's pick a distribution for this set intersection problem. Let's say this is a hard distribution. That distribution, this target element is chosen uniformly at random. Okay. Now let's look at the protocol for this set intersection problem, and let's pi be the transcript of the protocol. I'm going to say that this pi is epsilon solving set intersection on this distribution if the following thing happens. Basically, an external observer that look at the transcript of the protocol can learn something good about the distribution of the target element. In other words, the target element was originally uniform, but if the players do their communication and there is an external observer that look at this transcript, the distribution of that target element is now different from uniform distribution by epsilon in total variation distance. Does it make sense? So I don't want to find the target element. I want to help an external observer to be able to say something meaningful about the target element. Its distribution is different from uniform by epsilon. And so we have to prove a lower bound for actually epsilon solving the set intersection as opposed to solving it. And just a quick remark. So epsilon solving as an algorithmic problem is much easier than solving the problem with probability of success epsilon. Okay? Why? If you solve the problem with probability of success epsilon, Bob can just write the answer in the transcript with order log n more bits. And then after that, for an external observer, with probability epsilon, all the mass is in one element. Okay? So your distribution is distorted from uniform by epsilon already. But that's not the only way to epsilon solve the problem. What you can do is to look at the probability mass of target element, reduce it by epsilon over n for half of them, and increase it by epsilon n for the other half. Okay? This will change the total variation distance completely, but basically you didn't make much progress. So in that sense, this is actually harder than solving the problem with probability of success 1 plus epsilon divided by m. If I just shift the mass, of the distribution like this, the maximum probability of success that I'm going to get is just 1 plus epsilon divided by m. Good. So where do we stand with this? The first task we know is a hard task. It actually, Mark and others showed that it requires omega epsilon m communication. The second task is almost trivial. You just need to send order 1 bits. Just sample order 1 of yours input and send it to the other player. You can solve it with some non-trivial probability. Okay. So where does this problem stand? What we proved is that it requires omega epsilon s squared times m communication and also information. Believe again the correct answer might be still that, okay, but I'm not sure. Okay. Very briefly, let me tell you how the proof works. It's not that hard basically. The only thing is that let's look at two types of protocols. One protocol is able to just say that these epsilon m elements are not the target, okay, and shift all the mass to the remaining. That protocol is easy to handle. That protocol is basically removing epsilon fraction of your input as being useful. So in some sense, very informally, if I repeat it 1 over epsilon times, it can just find the target element for me. It each time say that these epsilon fractions are not input. I repeat it 1 over epsilon time, it just said that this is the final element. Very informally. The bad case is when the protocol takes your element, just increase the mass of half of them on 1 plus epsilon and the rest 1 plus epsilon. Reduce it by epsilon. Sorry. Takes your element, increase the mass of half of them by epsilon over n and decrease the other one by epsilon over n. And what we are going to prove is that actually this epsilon solves the problem, but if you want to make such a change in the distribution of the target element, you have to do a lot of communication. Okay. And then, yeah.
I think if you partition into blocks of length 1 over epsilon squared and send the majority of each block, you will actually epsilon solve such intersection. And upgrade the ones where majority.
No, say that again, sorry.
So partition the input into blocks of length 1 over epsilon squared. And Alice and Bob each sends the majority of each block, the majority bit of each block.
Okay.
Upgrade the 1, 1 blocks, downgrade the 0, 0 blocks, and leave the other ones alone. I think it epsilon solves that intersection. So
You are giving.
this is tight, the epsilon square.
I see. Okay, let's try. Yeah,
Well, that matches the
yes. Okay. Let me think about it. Okay, but good. Okay, so if you do that, and then you can go back and change the argument, and then work, this is going to give you a lower bound of ms squared divided by k squared communication. Okay? And then basically we are done. When you prove the lower bound for that problem, we use these reductions and get what we want. So let me conclude quickly. So we addressed this basically technical question that for these graph problems that have a small communication complexity, we wanted to have a technique that is allowing us to prove communication lower bounds for a large number of rounds, polylog n roughly. And then by doing that, we use that to get result for these different problems such as flow, minimum weight cut, and exographically fair semis. And this was a way that we get away from this log n pass barrier that was in previous techniques. And so if you go back and look at this regime of problems, well, we didn't know how to prove lower bounds here. We proved something, so now we know something happening is in this middle regime with the algorithms which use a relatively not too large number of passes. There were some open problems here that people cared about to know what is their true complexity. And now at least for maximum flow and min cut, we have some good lower bounds relatively. We know that they are not here. They are more to the right. What about the other problems? We do not know yet. I had some recent progress in these 3 other problems. It seems that similar techniques can be made to work for them. There are some combinatorial construction barriers that are needed to overcome, and it seems we can bypass it, but I don't want to claim anything, so we may not know anything for them. For random walk, which I think is a very interesting problem, we don't know anything at the moment. Basically, that's all I wanted to say. Thank you.